In this lesson, we are going to do two Taylor series examples. In the first one, we are going to find the Taylor series for the exponential function f of x equals e to the x, centered at x equals 0. We will also find the radius of convergence. Then in the second example, we are going to use our first computation to find a Taylor series for this function g of x, which I'm defining to be the integral from 0 to x, e to the t squared dt. This is not an integral that we can compute by hand in terms of elementary antiderivatives. So we will see how to use a Taylor series to approach this problem. And then, given that we can't even do this by hand, what we will do is use the Taylor polynomial t sub 3 to estimate the value of g of 1. So I'll show you how to do that. Before we jump into this first example, I just want to make a vocab remark. I always say Taylor series, but in the common situation of computing a Taylor series centered at x equals 0, I just want to mention, because you might see it, that these are called Maclaurin series. So I will continue to say Taylor series centered at 0, but you might also see this language. All right, let's find the Taylor series for e to the x centered at x equals 0, or in other words, the Maclaurin series for f of x equals e to the x. This is probably the easiest Taylor series to compute. And the reason why is if I write down the function f of x equals e to the x, I now need to start taking derivatives in order to look for a pattern that's going to allow me to describe, say, the Taylor coefficient c sub n. But every single derivative of this function is e to the x. So we found the pattern. It's always e to the x. That means that when I plug in the center to get the numerator for the Taylor coefficients, it's going to be e to the 0, which is 1. So the Taylor coefficients, c sub n, are this divided by n factorial. So they are 1 over n factorial. Let's write down now the Taylor series for e to the x. It's going to be the sum from n equals 0 to infinity, this coefficient, 1 over n factorial, times x minus 0 to the n, but that's just x to the n. This is a pretty famous Taylor series. If you start to write it out, when n equals 0, we get 1. When n equals 1, we get x. Then x squared over 2, or x squared over 2 factorial. Then x cubed over 3 factorial, etc. Let's find the radius of convergence for this Taylor series. For this, I'm going to do the version of the ratio test that just involves looking at the coefficients. So let me do the limit as n goes to infinity of cn plus 1 divided by cn. Okay, so that's going to be the limit as n goes to infinity of 1 over n plus 1 factorial times n factorial over 1 multiplied by the reciprocal. This is going to be the limit as n goes to infinity of 1 over n plus 1, since n plus 1 factorial is n plus 1 times n factorial, and that cancels out here. But this is 0. This version of the ratio test tells us that the radius of convergence is the reciprocal of this number. In the situation where this number is 0, that tells us that the radius is infinite. So this expression actually converges to the exponential function e to the x for the whole real number line. So this is valid for all real numbers between negative infinity and infinity. At this point, we've found the Taylor series for e to the x. Going to step away and give you a couple seconds to finish writing this down. I'm going to just put up for a few moments a visualization of this convergence. So you will see the function f of x equals e to the x together with the first few Taylor polynomials. So t sub 0 is just the number 1. Then t1 is 1 plus x. T2 is this quadratic 1 plus x squared over 2. T3, the third Taylor polynomial, if this is the zeroth, is this cubic polynomial. And what you will notice is that around the center at x equals 0, the convergence is clear. But it will not look like we are getting convergence from negative infinity to infinity. What this is saying is that if you want to approximate e to the x for any value of x, you can do that with this series. But the farther away you are from x equals 0, the more and more terms you need to take in order to see what looks like an approximation. Another way to think about that is no polynomial. So if I take any partial sum here, it's a polynomial. No polynomial can give you a good approximation of the exponential function on all real numbers from negative infinity to infinity because exponential functions and polynomials do not behave the same way. Notably, they have different end behavior. So e to the x has a horizontal asymptote to the left as x goes to negative infinity, whereas polynomials grow to either plus or minus infinity in either direction. So while this convergence is valid on the whole real number line, the farther you are away from the center at x equals 0, the more and more terms you need to take in order to get a Taylor polynomial which looks near that value of x, similar to e to the x. Let's use the Taylor series that we just found for e to the x to write down a Taylor series for this function g of x, which is being defined as the integral from 0 to x e to the t squared dt. This is not a function that we can write down in terms of nice elementary antiderivatives. So anytime you want to tackle this kind of integral, you have to use some sort of technique. And the technique here is going to be to use the Taylor series for e to the x. Okay, so let's do that first, and then we will discuss the second part of this problem, which is approximating the value of g of 1 using a Taylor polynomial. In other words, just taking the first few terms from our Taylor series expansion. Okay, let me write this integral. I'll just rewrite it as it is the first time. So we want to go from 0 to the input x for the function g, e to the t squared dt. Now I'm going to take this integrand, e to the t squared, and I'm going to plug the expression t squared in for x in the Taylor series for e to the x. So what that will look like is the integral from 0 to x, the sum of the series that we just found, so 1 over n factorial, except instead of writing x to the n, I'm going to write this exponent t squared to the n. Now let's write that one more time, and then we will anti-differentiate. So this is the integral from 0 to x of the sum from n equals 0 to infinity, 1 over n factorial t to the 2n dt. Okay. We've discussed in the past that you can integrate and differentiate power series to get to new power series. So this is an example of integrating a power series in order to arrive at a new one. We will take this expression here and anti-differentiate it. We're integrating with respect to t. Make sure you don't get mixed up with the n here. So we do this antiderivative now. It's going to be the sum from n equals 0 to infinity, 1 over n factorial. And then the antiderivative of this will be t to the 2n plus 1 divided by 2n plus 1. So it's just the power rule. And then this was a definite integral where the top bound was the variable x for the function g, and the lower bound was 0. If I plug in my top bound now, I have a power series expression that looks like the sum from n equals 0 to infinity, 1 over n factorial. Let me also write I'm going to make this just one big coefficient. 1 over n factorial times 2n plus 1. Okay, so that's the coefficient, x to the 2n plus 1. So that's what we get when we plug in the top bound. And then if I plug in x equals, or t equals 0 rather, every single expression in the series expansion has a t. So we would say minus 0. Okay, so that means that our function g of x now has this power series representation. So we can think of this integral that we cannot do by hand as alternatively having a power series representation that we can present instead. So this would be the sum from n equals 0 to infinity, 1 over n factorial times 2n plus 1, x to the 2n plus 1. Because we got to this through the action of integrating a known power series with a known radius of convergence, we don't have to do any work here to figure out what the radius of convergence is. It's inherited from this. The radius here was infinity, so here we also have convergence on the whole real number line. Okay, so that is the power series representation now for this function. Let me give you a minute to think about this, and then we will approximate the value of the function g of x when x equals 1 by just taking the first few terms here. So we will write down the Taylor polynomial t sub 3. Okay, so the true value of g of 1 is what we would get if we plugged x equals 1 into this series to produce an infinite series of numbers. But that's not that easy to work with either. So instead, what we will say is g of 1, setting x equal to 1, is approximately, a partial sum for this series. And I've chosen here the Taylor polynomial t sub 3, which means add up from n equals 0 to 3, this expression with x equal to 1. So that means that we're really just looking at adding up the first few coefficients, since 1 to the 2n plus 1 is 1. So t sub 3 of 1 is going to be, if you plug in n equals 0, you get 1. Plug in n equals 1, and we get 1/3. Then plug in n equals 2, you get 2 times 5, so 1/10. And then finally, plug in n equals 3, we get 7 times 3 factorial, so that's going to be 1 over 6 times 7 is 42. All right. If you add those up, I did it in my notes. This is approximately 1.457. Okay, so that's an example of using a Taylor series to approximate the value of a function, which is very hard to work with.